Hi guys, I'm really excited today to launch my new package ConfusionTableR. The aim of this was to tidy the outputs of a confusion matrix for storage in databases. I've had the opportunity to work on many machine learning models in my time, in my career, and I've done a lot in R and a lot in Python and a lot in deep learning as well. But in terms of supervised classification problems, confusion matrices are the kind of de facto way of assessing accuracy, how well the predictive value of certain metrics are in your database and in your machine learning model. So what I'm going to do is I'm going to launch into how we actually use the package. So as you can see on the screen, we've got this index that we can refer to in the package vignette. ConfusionTableR then pops up and we're ready to go. So like I said, what we're going to do is we're going to load some data in from a binary and a multiple classification problem. We're then going to fit a machine learning model. Finally, we're then going to save one of those machine learning models in a SQL database. So first of all, I'm going to load in my packages. So I'm going to work with Caret, dplyr, mrbench, tidyr, and E1071 and random forest. I'm going to load in the iris data frame, which is a traditional example of a multiple classification problem. Looking at the iris data set, we can see that we've got a species label, which is a classification label, the thing we're trying to predict based off the retrospective data. And these other independent variables, so sepal length, sepal width, petal length, and petal width. So we're going to use these observations and the variance in these observations to try and predict what species of flower it belongs to. Oops. So you can see we've got quite a nice balance in our class labels. So we've got 50, 50, 50. A lot of the time we're doing with classification problems, you spend a lot of time dealing with something called classification imbalance. Again, if you wanted to learn a bit more about imbalancing and rebalancing a class, I've done an advanced modeling webinar that's also available on my YouTube channel. So what we're going to do now is going to create a data partition, and we're going to use the species, the classification label. We're going to split it, so we're going to use 75% of our data on for the training and 25% on test. We're going to create a variable called train, and we're going to pass in a row level selection of that data frame. I'm going to select the front part of it, so I'm going to select the 75% of the rows. And this minus here means get the other 25% essentially. So we're going to run that, and now you can see we've got this train and test data set that's been created in memory. And it has done that 75. So if you did that on a calculator, that would work out at 114.36. What we're going to do now is we're going to use Caret's train function to train a random forest model. And we want to expose the accuracy, so we want to get the most accurate model based on species. Again, I'm not going to go into depth around machine learning here. This is more around how you utilize the confusion matrix tool. Please look at my tidy models webinars and my advanced modeling webinar in Caret. You can see that my accuracy now is around about 93%, which is relatively good in terms of classifying a multi-classification problem. So, it's going to select the best value, best accuracy. So we're going with this one at this number of random splits in the random forest. So in Caret, there is a function called confusion matrix, but I'll take you through what I'm going to do first of all. So I've got this trained model, and we've got this trained model called the RF model, random forest model. You can expose that to see all the training attributes. We're going to specify new data. So we're going to use the testing data, the proportion of the data set that we partitioned off to test our training predictions over our ground truth labels, which are the testing labels, the testing class species. I'm going to specify the type is equal to raw. There's two types that you can pass, raw or prob. Raw will give you the raw class labels that it exposes. So if I ran that and we had a look to see what that's done, you've got this RF class function which has created this prediction of a three-level prediction based on what species they belong to. We're then going to create a predictions data frame. So what I'm going to do is use the RF class that we just fitted here, these values, with our ground truth labels, which are the species. You can see the predictions is now run. We've got these training predictions and we've got our ground truth labels. So a lot of the time, once we've done this process, we actually analyze it via a confusion matrix. And you can see that I'm doing pretty well here in classifying the species, getting 97% accuracy. My sensitivity is pretty good as well. So yeah, based on that testing data, it's pretty good. And the kappa rate's good too. So yeah, things like sensitivity are how well it is at predicting the actual species, and specificity is the other side of that. So is it balanced in terms of not predicting the incorrect species as well? So say we're going for Setosa, we've got a sensitivity of 100% because actually all values are correct. If we had a little bit of imbalance here around the mispredictions, etc., your specificity rate would start to fall as well, because it's how good it is at predicting the thing you're trying to predict, how sensitive it is at predicting the class label. And in terms of the specificity, it's how good it is also accommodating for the things on the class label that it's trying to predict. I'll put a link into all these metrics and the descriptions as part of this blog, part of this YouTube tutorial and the associated blog. So now we've got it in this format. This is actually a list format. If you can see, we've got a list of 6 values, which is interesting and nice, but I want to collapse this list down. And this is what the ConfusionTableR package does. So because this is a multi-classification problem, we're going to collapse it down using the multi_class_cm function. And all this needs is the training predictions and the test ground truth predictions to make it work. So we're going to run that. And as you can see now, instead of having this list, we've got a row-wise list that we can store in a database. So why would we want to store this confusion matrix in a database? So over time, if certain features in that model change, so if you're putting it into production live, certain features in that model change, there's something called feature slippage. So actually, if the encodings underlying the values start to slip, or the accuracy level starts to depreciate, if you've got it in a database, you could set some alerts up to say, actually, the accuracy is declining, so do something, please reinvestigate the model training schedule, etc. So it's also good to have an audit log of the predicted values as well, and how well your models fit as part of the training cycle in terms of your machine learning pipeline or your predictive pipeline. So this is what it essentially exposes. Instead of having all those, it would be lots of rows and lots of columns. It flattens it down to one row of 50 columns. Okay. So I want to then, the good thing about the ConfusionTableR is there's no need to fit this confusion matrix prior. You can essentially get rid of this step, these steps here, or these 2 steps, because inbuilt into the ConfusionTableR function, it actually exposes the original confusion matrix object. So what you have to do is, when you fit this multi-class or this ConfusionTableR multi-class confusion matrix with these past values, you get the record level confusion matrix, which we've just been talking about, and you also get the original confusion matrix that's present in Caret. You can also extract just the data table from that, the predictions table. So this is really useful. It means that actually you can use ConfusionTableR instead of using the default confusion matrix, because it allows you to expose a confusion matrix and also store it in databases at record level. So say that's for a multiple classification problem. So when we've got multiple dependent variables or multiple labels we're trying to predict. What we're also going to do is we're going to use it on a binary classification task. So this task is a cancer data set, a breast cancer data set, and it comes from the ML package, ML bench package. We're going to get rid of the NA values, so we're going to use complete cases. We're going to chop out one of the items, one of the columns from there. We're going to set the class variable, which is whether it's benign or malignant, to a factor, and then we're going to run this. Okay. So we've got this prepared data now. We've got this breast data set. And just to view it, we've got cell thickness, cell size, cell shape, the adhesion of the cell being nuclei, chromatin, nuclei, and mitosis, and the class, so whether it's benign or malignant. So we're going to use these retrospective patterns like we did before to try and make a prediction about future values or future patterns that the machine learning model observes. So we're going to then predict the class labels. So we're using this same create data partition function that we've previously seen. I'm not going to go over that again. We're going to fit the caret model to a random forest. And again, this auto fits based on the best high parameters, thus why I like caret. It allows you to predict based off this new random forest fit. We're going to pass in the new data test and we're going to expose the raw predictions. We're then going to do the same here. We're going to combine the class predictions from this pred, so the raw predictions of the training labels on the ground truth testing labels. Okay. So this will take a couple of seconds longer than the previous example that we looked at, just due to the size of the data. Okay, so the model's now fitted. So now we're going to do the same as we did prior, but this time I'm going to use the binary underscore class underscore CM from the ConfusionTableR package. We're going to pass in the predicted trading class predictions and the ground truth labels from the testing set. And then once you've got this as a list, so the Confusion binary class R will return a list item. To actually grab the list items from that variable that we've just created here, there's also these options. Look, there's the original confusion matrix, the record level confusion matrix, which is the row by row one that you've seen, the table, and when it was run. So if I just run that, you can see that now I've got this row-wise list, which is perfect for storing in a database. If I just glimpse that, I've got one row and I've got 23 columns. So I'm good to go. And the next example, I'm going to show you how I'm going to store that in a SQL Server database. Finally, the final option in ConfusionTableR at the moment is the binary visualizer. So it actually creates a binary visualization table based off our binary predicted variables, so our class predictions, so the training predictions, and the truth label, so what the actual ground truth label was, which is the testing class. So we're going to compare what we've predicted versus what we know. We've got benign and malignant as the labels, and we're setting colors. These can be reset. You can set them to whatever you want. Red. Yeah. Green. You can see that the confusion matrix starts to change. You can give it a custom title, my custom confusion matrix, whatever. Yeah, and that will change. You can even change the text color, so let's make it white. So you've got white text then. And it'll give you all the summary statistics at the end of that as well, so you can view it. And again, they're all the ones that are captured in the confusion matrix. So what we're going to do finally is store the confusion matrix outputs in a database. So again, like I said to you, time after time, you want to monitor your model training performance over time. So this was the reason why the ConfusionTableR package was created. So I'm going to load in the DBI package and the ODBC package, which are packages that allow you to work with databases, all different types of databases. I'm going to work with SQL Server, but it works with a multitude of other types, such as MySQL, etc. If you want help on any of these functions, like you say, you can call help on each one of those functions. It's quite easy. You just go binary visualizer. That will give you help on that specific function. It shows you what needs to be passed, examples of how you implement the function as well, as we've gone through today. Okay, so that creates that for you. And if you need to install this package, it's directly available from CRAN. So you can install it by searching for it in the package list. And you can see it matches on CRAN. There's also a Ubuntu and a Linux version as well. So library DBI and OBC. We're going to use this write table function that I've created, and I've linked in the GitHub, so you can use this function if need to. going to have a driver, so the driver to connect up to our server, the database, whether it's a trusted connection or not, the schema, and a table. And essentially we're going to get all these values and return them in the function. It's going to print out some messages. And then you're going to DB write table. So you're going to use the connection, the ID, and we're going to use append and overwrite. And it'll say that it's finished. So finally, this is the fun part. I'm going to use my binary classification model because I know that I can keep appending that onto a data table. I'm going to use a binary classification model as an example. And I'm going to store that in the database table. So my driver is a SQL Server. I've got a SQL Server instance set up here. My server is localhost and SQL Express because I've created a SQL Express database install here. My table name, so my database name is the R database. And then what I'm going to do is I'm going to create an object. So I'm going to run these lines here, Control and Enter. And I've got this binary classification table, which is that row level classification table that we've seen before from the confusion matrix. And then what I'm going to do is I'm going to use my write SQL function I've just created, pass it in the driver, pass it in the server, and pass it in the database. If I didn't want to create variables, this would be SQL Server, this would be localhost SQL Express, and this would be our database. Our schema is equal to data. We're going to pass in the table, which is this object, the R object. We're going to use the append because we want to keep appending data to it. I'm going to use the table name equals to the breast cancer confusion matrix. So if I run that, and I've not done that, I've not run the function, school error. I'm going to run this. As you can see, I get a message establishing connection to localhost, writing the database, please wait, and then finishing writing to database, our database. It will pass our database that you passed in 0.08 seconds. Pretty quick. So if I just refresh my database, I should see this breast cancer confusion matrix now. So you can see my last entry, if I check the timestamp, is around here. So actually, yeah, it's finished writing and it's passed in the accuracy. And I've got this record now over time of the different predictions. So you can see based off the random nature of how it partitions in Caret, that I've got different accuracy values, but it seems to be hovering around 96%. So actually it also allows you to build up what the true average rates are of these over time based on different partitions. So you can then monitor that going forward. And that's really the motivation for the package. And that's why if you're a machine learning practitioner, it's really important to monitor your models over time. So wrapping up, again, like I said, I've create this package to aid in the storage and creation of confusion matrix outputs into flat row-wise structures for storage in data tables, frames and potentially data warehouses. And I tend to monitor these statistics for working with these metrics over time so I can calculate their relative averages, etc. as the model retraining happens. So just give you an example of a model retraining cycle. Say you retrain your model every 2 weeks, then you'll get a log every 2 weeks. Then over time, if the accuracy starts to dip lower than what we have around 95%, say 90%, you could actually put a little SQL trigger or something like that to say you need to review your model training scheme. There's something wrong. It's starting to deviate in terms of model performance. And that's really, truly the motivation behind it. So thanks for watching the tutorial today. Please download the package from CRAN. It's also available on my GitHub. I'll just bring that up in a second. So the package is available on my GitHub. You can find that it's actually the newest version. It's just been published today. I've just done the last commit. And because it's been running for a while, I have this one in my GitHub repository. I've got quite a few people that already use this package. So it just shows you how to use it with a link to the associated vignettes. So I'll put it on all pubs and it will go through exactly the same examples that we just detailed, bar the writing to SQL Server, which is a new add-on that I've just added today. And again, yeah, it will just show you how to do that. And if you want an example of the make SQL table function, this is where it is. It's at DBI large data. That'll give you the function here, and this shows you how to use the new function. So I'm using a data set from NHSR datasets that we created as another CRAN package to do that. But yeah, guys, please download it from CRAN. Please subscribe. I've really enjoyed taking you through this today, and I hope to see you soon when I put out a few more packages or make amendments to my existing ones. All right, guys, have a great day. Stay safe. I'll see you all soon. Oh, and subscribe.